I thought I would just recap a little bit about what we did last time, and there was a question yesterday at the review session something that I'm not sure I made clear. But last time we had these 3 theorems. I could have written them all down as special cases of one theorem, but I didn't want to have some huge abstract thing. But the first one is the inverse function theorem. And it deals with a map from Rn to Rm, so the 2 dimensions are the same. And it says if the derivative is bijective, then the function itself is bijective locally, nearby. And the second one has to do with a map from Rn to Rm plus n. So this dimension is smaller than this. And this one says if the derivative is injective at some point, then the function itself is injective nearby that point. And the submersion theorem says that here we have a higher dimension here than here. And it says that if the derivative is surjective, well, if this is really the statement that we're going to use the most. If it's surjective at each point in the level set, then the level set is a smooth n-dimensional manifold. So one thing I wanted to say was that in each case, the hypothesis is that the derivative have maximal rank. So in the first case, it's an n by n matrix, right? And the n by n matrix is bijective if and only if it has rank n, right? In the second case, in the immersion theorem, the derivative is an n by n plus m dimensional matrix. And the condition that this be injective is exactly that this have maximal rank, which would be, in this case, n, right? And finally, the submersion theorem, the condition that this derivative be surjective, this is a n plus k by k dimensional matrix. The condition that this be surjective is exactly that this should have maximal rank. And I guess the other thing that I wanted to point out is that these 2 theorems, well, the first theorem has something to do with change of coordinates, and the second and the third theorems have to do with ways of describing a submanifold in Euclidean space. So there are 2 basic ways to get a manifold in Euclidean space. You can either look at it as the image of an immersion, or you can look at it as the pre-image under a submersion. And in the submersion case, the fact that this is surjective is basically saying that you have k independent conditions that you're imposing on n plus k variables. And the fact that this has maximal rank is saying that those k conditions are independent of one another. OK, so I wanted to do one more example before I go on to start talking about geodesics. So let me just remind you of the last example I did last time. Was the following thing. We looked at the sphere S2 inside R3, and we showed that this was a smooth manifold using the submersion theorem. And we also looked at the level sets of the height function of the function h of x, y, z is equal to z in local coordinates on the sphere. Local coordinates near the North Pole on the sphere. And we saw that the level sets look like this. It's not surprising, but we looked at it in local coordinates. We see that there's actually a local maximum, right, of the height function, as there should be, right? But you can tell from the level sets that there's a critical point there. So the last example I want to do is this sort of a slightly more complicated version of this. So it's a similar kind of construction. So for this one, I want to look at the set S, which I'm going to call S. It's the SL2R. So this is the 2 by 2 matrices of determinant 1, right? So it's the set of all matrices of the form A, B, C, D, such that AD minus BC equals 1. Okay, so you can do this example in higher dimensions, but I think it's good to see it in lower dimensions just to see what's happening. So this is a group of matrices, and It's important for a lot of reasons. I actually started looking at it because I was looking at closed geodesics, and I was looking at the geodesic flow, and this naturally, symplectic groups naturally, this is actually SP 2 times 1 R also. It's also a symplectic group. So that's how I originally became interested in this. The determinant is not a very interesting function on this group because the determinant is always equal to 1, right? But the trace is an interesting function. So trace is an interesting function on SL. Let me just call it S. So for example, if you write down the characteristic polynomial of one of these matrices, right? You get determinant of A minus lambda D minus lambda BC, right? If you take the determinant of that, you get AD minus BC minus lambda times A plus D. Let's see. What's the constant term? Here's the constant term, and then I have plus lambda squared, right? Right? And this is equal to 1, right? And this is equal to the trace. A plus D is the trace. Does everybody know what the trace of a matrix is? It's the sum of the diagonal elements. Yes, everybody knows that? Okay, so if you this is a quadratic equation, and if you solve this quadratic equation, you see that the eigenvalues depend upon the trace. So if the trace is bigger than 2, then the eigenvalues are R, 1 over R, for some positive number R. Let's say R bigger than 1. And if the trace equals 2, the eigenvalues are 1. They're both 1. If the trace is between minus 2 and 2, then the eigenvalues are e to the I theta and e to the minus I theta. And if the trace is less than negative, well, if the trace is equal to negative 2, they're minus 1 and minus 1. And if the trace is equal to less than minus 2, then they're minus 1 over R and R, for R bigger than 1. So the trace is really giving a lot of information about the matrix. It tells you basically determines the eigenvalues.
So you mean minus 1 over R minus R?
Yes, thank you. All right, thank you. Okay, so we're going to look at this again. We're going to think of SL2R, and we're going to think of it as being a surface. So S is a surface. It's in R4, right? So what is it? So here's the definition of what it is. So what do we have to look at? So we want to show that S is a smooth manifold. What should the dimension be? What should the dimension be? We have 4 variables, right? A, B, C, D are the 4 variables. How many equations? 1 equation, right? So what's the function? The function is F is a map from R4 to R1. What's F? F of, well, we can write these 4 real numbers in a square, or we can write them in a column. It's basically the same thing. So F of A, B, C, D is AD minus BC. And then S is just F inverse of 1. So in order to check that it's a smooth manifold, what do we need? We need to check that on the level set, right, F inverse of 1, that there are no critical points. So we need to show there are no critical points on the level set. F inverse of 1. Okay, but what's the derivative? What's the derivative F prime? So we have to differentiate with respect to A, differentiate with respect to B, differentiate with respect to C, differentiate with respect to D. So we get it's D minus C minus B A, right? That's the derivative. And the condition that we need is what? That has to have maximal rank, right? What's the maximal rank of a 1×4 matrix? 1, right? So in maximal rank just means that it's not completely 0, right? So this has maximal rank unless, right? Unless all these guys are 0, right? A equals B equals C equals D, unless they're all equal to 0. But in this case, F is equal to 0, right? So it's not on the level set. In which case, the point A, B, C, D is not in S. Okay, so this computation shows that this is a smooth manifold of dimension. I didn't say the dimension. What's the dimension? 3, right? 4. We start off with 4 variables, and we have 1 independent equation. So it turns out to be dimension 3. So okay, so we showed that 1 is a regular value. Okay, so now the thing that I was interested in was looking at the level sets of the trace function. The trace function is interesting, well, again, mainly because it determines the eigenvalues. Also, maybe I should point out that the trace function is constant on conjugacy classes. Right, if you conjugate a matrix, you don't change the characteristic polynomial, and you don't change the eigenvalue. So it's, of course, the trace is the sum of the eigenvalues, right? Does everybody know that? Yes. Okay. So here's the question then: is what are the level sets? What do the level sets of the trace function? So this is A plus D look like on S? So again, it doesn't look like a very interesting function, right? It's not, and in fact, in R4, it's not a very interesting function, right? But so what does it look like on the group SL2R? Well, what we need in order to look at it in local coordinates, we need a parameterization. So we need a parameterization. And I'm going to do this near the identity. So what do the level sets look like near the identity matrix? So how do I get a parameterization? Well, I wrote down the following thing. G is a map from R3 to R1. So G of U, B, C. So B and C are going to be 2 of the coordinates, but I'm going to do something else with A and D. So G of U, B, C is the following thing. It's U plus the square root of 1 plus BC plus U squared, and then B and then C, and then minus U plus the square root of the same thing, 1 plus BC plus U squared. How I came up with this, I don't actually remember, but what do we see? So this is a map from R3 to R1. I'm sorry, it's from R3 to R4. Sorry. And what about the image? What about the image? Does it satisfy the equation? Does it satisfy AD minus BC equals 1? If I wrote it down right, it should satisfy this, right? This times this is going to be your A, this is going to be your D. This times this minus BC. Right? Does that work? This times this. It's a difference of 2 squares. So it's 1 plus BC plus U squared minus U squared, right? And then we subtract BC, so it does satisfy this equation. Show.
Did anybody lose a backpack? No? It was left at security.
yeah.
So is anybody going to stare? Well,
She's in
we
my
leave it
area.
back here and just tell her that it's here? Okay.
Yeah.
Thanks, Michelle.
Yep.
All right, so this is a map from R3 to R4, and you can check that it's actually an immersion. Shall I do that? Let's see. Right, so what I need to compute is actually g prime of 0. Let me just write down what it is. G prime at 0, 0, 0. So, oh yeah, what should I say? What the image of 0, 0, 0 is g of 0, 0, 0 should be the identity map, right? Is that right? Right, this is 1, 0, 0, 1, right? This is the identity matrix, right? A, B, C, D. So g prime of 0, 0 is the following matrix. It's 1 plus u divided by the square root of that stuff, and then c divided by 2 times the square root of that stuff, and then b divided by 2 times the square root of that stuff. 0, 1, 0, 0, 0, 1. Minus 1 plus u divided by the square root of stuff. C divided by 2 square root of stuff. B divided by 2 square roots of stuff. And at 0, 0, 0, so I have to evaluate this at 0, 0, 0, 0, 0. And what do I get? And what properties am I hoping that is going to have?
It should have rank 3.
It should have rank 3. Right, and in fact, it's equal to 1, 0, 0, 0, 1, 1, minus 1.
0, 1, 0.
Yes, thank you. 0, 1, 0? No. Oh, I missed 1, right? That's my problem. 0, 0, 1. Okay. Right. Yes?
Yeah.
And in fact, it does have rank 3, right? Rank 3. And why is that good? That shows that this is a submersion, right? Immersion. This shows that this is an immersion, right? So G is an immersion at least near the point 0, 0, 0. So G is an immersion near the point 0, 0, 0. And that says that it gives us good local coordinates, right? So we can use U, B, and C as local coordinates on our manifold. So U, B, C are good local coordinates. And now what's the function we're interested in? The function we're interested in is the trace, right? Right, the trace function. So what is the trace function? What is t? So in terms of these coordinates, what's t? T is a plus d, right? So it's this plus this. So t is equal to the square root, well, 2 times the square roots, right? 2 square roots of 1 plus bc plus u squared. And the level sets of that are the same as the level sets of, well, bc plus u squared, right? This function is constant exactly when this function is constant, right? And the level sets of this are what? We're now in R3, right? Because we're using these local coordinates. We're using the local coordinates u, b, c in R3. This is I don't know quite what it is, but it's definitely a quadric surface, right? It's a polynomial of degree 2 and 3 variables, so it's a quadric surface. It's not in standard form, but I can get it in standard form by a further change of coordinates. Change of coordinates. I'll leave you to explain why this change of coordinates is okay. I'm going to have b equal to u minus w, and c equal to v plus w. Oh, this is v minus w. So I'm exchanging b and c for v and w, so we just need the rank of this matrix to be 2, right? Which it is, you can check. And so what do we have now? What are the level sets? The level sets are, if we bc is v squared minus w squared, right? So the level sets of trace are given by v squared minus w squared plus u squared equals constant. We did this yesterday, right? We sketched the level sets of this. These are, anybody remember what this looks like? There's a cone, right? The cone is where trace equals 2. Here's the identity matrix. And there are these hyperboloids of 2 sheets, right? There's an infinite family of hyperboloids of 2 sheets. Here the trace is less than 2, or remember, this is just a local picture near the identity. This is not the whole symplectic group. This is just a piece of the symplectic group near the identity. So this is, here we have trace less than 2, and here we have trace less than 2. So the ones down here have eigenvalues that are imaginary, right? Or complex, right? E to the I theta, e to the minus I theta. And then we have the hyperboloids of 1 sheet where the trace is bigger than 2. And so here, for example, a typical matrix here would look like R 0, 0, 1 over R. A typical matrix here would look like cos theta, sine theta. There's a sign. I can't guarantee that the sign of this is right. Maybe Dusa knows.
Well, if you want to, minus sign.
I have the sign wrong?
Well, it depends if you want to rotate it
Yeah.
back through theta. Well, in that direction, then it's correct.
It's correct. All right. So this is a plus direction. Is that right? Yes? Anyway, there. All right. No, it's okay. There's some sign involved with this. And this is the most interesting one here, the level set of 2, right? There's the identity is on here, and it's its own conjugacy class, right? The identity is only conjugate to itself. But up here, there are these matrices like 1R, 0, 1, right? So these are not diagonal, and they lie on this open cone, right? So the conjugacy class of this is the upper half of this cone, not including this point. And there's another conjugacy class. Again, I'm not sure about the sign of the R, as I'm not quite sure about the sign of the theta, but there's another one down here. Okay, so again, this is an example where, this is something that you can do, right? If you have a manifold in Euclidean space, if you want to imagine what it is like to live on that manifold, you can get local coordinates by expressing the manifold as the image of an immersion, and then you get local coordinates, and you can actually do calculus on manifolds in Euclidean space. Okay, so now I just wanted to get started a little bit today talking about geodesics. So we've heard some talk already about geodesics. We had a nice talk yesterday by Regina, and I want to talk about geodesics on manifolds. So, what's the idea of geodesics? Well, geodesics have 2 sort of basic properties. The first property is that geodesics are straight. This is just a basic idea. So in physics, geodesic is the path that a light ray would take, right? So if you have a source of light here, you shoot out a light ray, the light ray will travel along what it considers to be a straight line, right? It'll go forward, and the geometry of space will somehow determine whether, I suppose it's possible that if you shoot out the light ray this way, that, I don't know, 3 years later, if you're standing here watching it, that it might come and hit you in the back of the head, right? It could happen, right? Depending upon how space is put together. So that's the straightness property. The other property that geodesics have is that they locally minimize distance, right? Minimize distance. So if you look at a light ray traveling along, and you look at it where it is at some time A, and if you look at some not too far away time B, that you'll find that between these 2 points it was the shortest possible path. So these are sort of the two basic properties. And again, the idea is when we talk about minimizing distance on a manifold, I'll tell you what I mean by being straight on a manifold in a minute, but what I mean by minimizing distance is the following thing. So distance on a manifold, all the manifolds I've defined here are submanifolds of Euclidean space. And if you know a little topology, I'm going to be assuming that they're inheriting the topology and the distance function from Euclidean space. So the distance on a manifold is measured so you look at curves on the manifold. The distance, let me just write it correctly. So the distance between 2 points, on a manifold M. And again, I'm thinking of it as being lying in some high-dimensional Euclidean space. So the distance between 2 points is the minimum length I'm going to say what I mean by that in a minute. Minimum length of a curve, continuous curve. Let's call the points P and Q. The minimum length of a curve from P to Q. Now the curve has to lie on the manifold. So the curve lying on M. But we take the distance from the Euclidean space. Right, so if you're on some manifold, let's say it's a two-sphere, for example, a two-sphere sitting inside R3, and you want to fly from Paris to Madrid, which I think is approximately the same latitude, right? You want to find the shortest path from London to Madrid. You're not allowed to leave the surface, though, right? We're staying on the manifold, but we're measuring the distance using the ambient space. So the length of that curve is measured as a curve in R3, but we're only allowed to consider curves that are actually sitting inside the surface. So this is what we mean by the distance between 2 points. Okay, so I mean, here's another example. So if just a very simple example, if you look at the circle in R2, if you look at the circle in R2 and you want to find what's the distance between this point and this point on the circle. So this is a circle of radius 1. This is the point 1, 0. This is the point 0, 1. On that circle, the distance between those 2 points it's not the square root of 2, it's what? Pi over 2, right? So the distance between these 2 points, distance between these 2 points is pi over 2. And what we're supposed to do is imagine that we live on this circle. And if you lived on this circle, we're imagining that you can't see the ambient space. All you see is the circle. So if you live on this, it's kind of boring to live on the circle. If you start out here, there's only one direction you can go, right? And if you lived on the circle and you started off on a path on this, you went for a walk, right? That you'd find after you went a distance 2 pi that you were back where you started from, right? Okay. So, all right. So now I want to define geodesics. I'm going to define geodesics on M, not using the straightness property. Using the straightness. And then we'll show that it actually has the other property, the length minimizing property. So how do I define a geodesic on a manifold? So I have a map gamma. So let's see. So path gamma from some interval to M. So I'm thinking of M as a manifold M is a manifold in Rn. And a path is a geodesic if it has the property that the acceleration vector, so maybe I should call this R equals R of t. Then we have the velocity vector, right? V equals V of t. And we have the acceleration vector, right? So this is dr dt, and this is dv dt. We have the velocity and we have the acceleration, and it's called a geodesic if at each point, at each time t, we have that the acceleration vector is perpendicular to the manifold. It's perpendicular to the tangent space, to M, at the point R of t. So the acceleration is perpendicular to the tangent space. So what does this mean? This means that gamma has the minimum acceleration needed to stay on the manifold. Needed to stay on it. Okay, so if we have a picture up here of our going along this curve, right? The acceleration here is pointed inward, right? The acceleration is perpendicular to the velocity vector at each point. And it's perpendicular to the manifold, right? So the tangent space at this point looks like this, and the acceleration is perpendicular to that. That's the minimum acceleration to stay on the surface. So this condition should be called straightness. So yeah, let me just write down the condition, right? So this condition here, this is called straightness. To stay on the road, right? Yeah. Okay. Yeah. Good point. Right. All right. So the first thing I want to show you is that geodesics exist. Theorem. So if you have a smooth manifold, and if you start at any point and you pick any direction, there's a unique geodesic. So let P be a point in the manifold, and V is a vector in, let's say, the tangent space at some point P to M. Then we're going to find, we will find a geodesic. So R equals R of t. So it's going to be X of t, Y of t, more if we have higher dimensions. So we want to find it starting at time t equals 0 at the point P with initial velocity V. So V is a tangent vector. So we have a point and we have a vector, and we want to show that there's a geodesic that starts at this point in this direction, at least for small times t. Small t, at least. Whether you can continue that or not, we can discuss that later. But so I'm going to just assume that the dimension of the manifold, that it's a two-dimensional manifold in R3, although that doesn't really change anything, just makes the notation a little bit easier. So we're going to assume that n equals 2. So we have a two-dimensional manifold. So we're a two-dimensional manifold in three-dimensional space. So 2D manifold in R3. And then by the implicit function theorem, which is a sort of a relative of the three theorems that I wrote up before, we can assume after rigid motions that the manifold is just given by an equation that looks like z equals h of xy. So we just assume that it's given by some height function, z is equal to h of xy, and we can assume that and that the tangent space to M at P is the horizontal plane, is the xy plane. Okay, so I'm just going to rotate things around until the surface has this horizontal tangent plane here. And okay, so now I want to write down the equations. So we have z equals h of x and y. So h is, I'm thinking of h as being the height function. This is the graph of a height function. Okay, so now if I differentiate this, what do I get? I get z dot, derivative of this with respect to t. So dot differentiate with respect to t. I get z dot is h sub x times x dot plus h sub y times y dot. Is everybody okay with that? The chain rule, right? Partial of h with respect to x times dx dt plus partial of h with respect to y times dy dt. So I get, and we can take a second derivative, and you take the second derivative, you get z double dot is equal to h x x x dot squared plus h x x double dot. Plus 2, hang on a second, plus 2 hxy x dot y dot. Right, so if we differentiate this, hang on a second, all right. So far so good. All right, so plus h y dot squared. I guess I rearranged the terms. That's why it doesn't look familiar. Right, so these are the ones where you differentiate the h's, right? These are the four terms when you differentiate the h's, and the terms that you get when you differentiate these guys are plus h sub x, x double dot, plus h sub y, y double dot. So we have this is z double dot. I'm going to put stars here. And basically, what is this these equations are saying that the curve stays on the manifold, right? So the curve stays on M, right? So R equals R of t, right? R equals x of t, y of t. And if it satisfies these equations, that's basically saying that it's not leaving the manifold, right? And then, okay, so meanwhile, note, so this is not the most sort of fancy way to do this, but I'm trying to do it with the most geometry with the least amount of machinery. So meanwhile, so this is an ad hoc, we notice that the two vectors, 1, 0, h sub x, and 0, 1, h sub y are linearly independent, right? No matter what these guys are, I think by our assumptions these are both 0 at the origin, and they're both perpendicular to the normal vector. The normal vector, what's the normal vector to the surface, right? The surface is given by z equals h of x and y, so the normal vector is the vector, the gradient of h of xy minus z. Right, the surface itself is a level set of this function, right? So we take the gradient of this, and we get h sub x, h sub y, comma minus 1, right? Right, so these two vectors are linearly independent, and they're both perpendicular to this, right? And therefore, so what's the condition? The condition is supposed to be that the acceleration is perpendicular to the manifold, right? So here's our normal vector, right? So what we need is that, so we need the acceleration to be in this direction, which is the same as saying that it's perpendicular to this and perpendicular to this, right? Because these three span at that point, right? If it's a multiple of this, if and only if it's perpendicular to this and perpendicular to that. So I write down those two conditions. And so what do I say? So it's a geodesic, which is saying that A double dot is perpendicular to M, if and only if it has the property that xy, x double dot, y double dot, z double dot, right, which is the acceleration vector, is perpendicular to both of those two vectors, 1, 0, h sub x, and x double dot, this is the acceleration, y double dot, z double dot, is perpendicular to the other vector, 0, 1, h sub y. I think I'm going to skip to the chase here. Right, so if you put all of this together, you get the following equation. You get x double dot, y double dot is equal to minus v hv plus times the identity matrix plus, this is a 2 by 2 matrix, hx hy times hx hy. You multiply those two together, you get a 2 by 2 matrix.
So the equation would be that the inverse is equal to 0.
Yes. Thank you. Okay, so identity of this times this is a 2 by 2 matrix. This is a 2 by 2 matrix, and I want to then take the inverse of that, apply it to hx hy, and multiply this where v is the vector, the horizontal component of the vector, so it's x dot y dot, and h is the matrix of second partials, so it's the Hessian matrix, hxx, hyy, hxy. I know you have to leave. hyx. You don't want to. Okay, all right, that's fine. Okay, so we get this equation. The interesting, what's important about this is that this is the identity matrix, right? And all of this stuff is 0 at the identity, so it's definitely invertible, right? So we can write this down. And so what do we have now? What we do now is we take this is a second order equation, second order differential equation, and second order differential equation in two variables. Right, the variables are x and y, right? So the z is going to follow because it has to, we're going to know the z coordinate because it has to stay on the manifold, right? So z will just be h of x and y. So and the usual thing that we do with such a thing is we turn it into a first order differential equation in 4 variables. Has everybody seen this before? Same kind of construction. So the variables are going to be x, y, and the velocity vectors, u and v. Right? So the position vectors and the velocity vectors. You do this in physics, right? When you whenever you have F equals ma, right? You get an equation for the acceleration, and you turn second order differential equation into a first order differential equation. And what it looks like is the following. It looks like d by dt of the vector x, y, u, v. What's important now is just what the form, just the general form of it. It looks like u, v, and then we have two functions, f of x, y, u, v, and g of x, y, u, v. So where x, these are given by, f and g are given by these equations here, right? So you plug in x and y for the position, and you plug in u and v for the velocity, and you get this equation. So what is this? This is a direction field, right? So this is direction field in 4 dimensions. Four dimensions R4. So we have 4 variables. And this is a vector field in 4-dimensional space. And what we're looking for is just the integral curves of that vector field. And this is Lipschitz continuous, and therefore there are solutions. Right, so this is, and again, the idea is just that it's a, you know what a vector field looks like. It's a vector field in 4-dimensional space, and you just want to follow the integral curves of that vector field. So the solutions exist. Solutions exist. And integral curves of this vector field, this nice vector field. Everything is smooth, right? And field. See, this part of the equation just says that if this is the position, then this is the velocity, right? The derivative of the position is the velocity. And then the derivative of the velocity is the acceleration. Right. And we wrote down an expression for the acceleration, right? This is an expression for the acceleration, right? And what these equations say is that the derivative of the position is the velocity, and the derivative of the velocity is this, right? Which is what we wrote down here.
How did you get that equation?
Which equation here? I left out some steps. Basically, I just solved this, right? So I'll tell you basically what I did. I wrote out this equation, and then I plugged in z double dot from somewhere else. Let's see, where do I get z double dot? I plugged in z double dot from here. Right. So I took this equation here, and so this gave me an equation x double dot, y double dot, and z double dot. Right? Yes? I plugged in from here. Yeah. Okay, good question. Okay, so this shows that the geodesics exist. And I guess another property, at least for small time, and an important property is that, Joe, I guess this is something you know from driving the sports car, that if the acceleration is perpendicular to the manifold, it's also perpendicular to the velocity, in which case what happens to the velocity? Who knows? Anybody know? The velocity, the speed is constant, right? So d by dt of the velocity, if we take the inner product of the velocity with itself, it's dv dt v, right? Plus v dv dt, right? If the acceleration is perpendicular to the manifold, it's certainly perpendicular to the tangent vector, right? Because the tangent vector is along the curve, and these are both 0, right? So that means it's constant speed. So geodesics have constant speed. And I guess the next thing I wanted to show is that they also have the straightness property. I'm sorry. They also have the length minimizing property, right? So we define here. We define. Maybe I'll just give the idea of that. So we define geodesics using the straightness property. And now we want to prove that they have the other property. Prove they minimize distance, they locally minimize distance. And I found a very nice proof of this in Milner's book. Milner's Morse theory book. This is the book where I learned everything I know about differential geometry in this slim volume. Right? I recommend it highly. Anyway, so let me just give you the outline of the proof. Okay, so here's lemma 1. I'm just going to state the two lemmas that prove it. So it says that the geodesics through P so if you take any point P in the manifold, the geodesics through P are orthogonal to the spheres. Let's see, I didn't define the exponential map yet, but if you start at a point P and you go out along a geodesic, let's just call it the sphere with center P and radius epsilon. So this is the sphere that I get by starting at a point P and going along a geodesic in all the possible different directions of length epsilon, right? So this is something like a sphere. And the first lemma is to show that that the sphere is perpendicular to these to the geodesics. Okay, so I think that's at least believable, right? And the second, so basically what this is saying is if you want to get, they intersect perpendicular at these points. And the second lemma which follows from the first lemma is that right, so the shortest path between two spheres is a radial geodesic. Sorry, radial geodesic. Okay, so we have the spheres defined this way, and what it says is if you want to get from one sphere to another sphere, the fastest way to go from one sphere to another sphere is by a geodesic through P, right? A radial geodesic. Right? So if these are perpendicular, right, then you would only lose distance by sort of moving one of them sideways. So again, it follows from this argument that if you want to get from one sphere to the next sphere, the shortest distance between these 2 points is in fact the geodesic that's between them. So that proves that geodesics also have the conclusion. And we'll stop. Conclusion. Geodesics, as we've just defined them, on a submanifold of Euclidean space. So first of all, they are straight, right? That's the definition, right? The straightness definition is that the acceleration is always perpendicular to the manifold. So they're turning the least amount, right? Given that they have to stay on the manifold, and also that they locally minimize distance and locally minimize distance. So what does that mean? It just means if you go along a geodesic and you take 2 points on the geodesic, and if they're close enough together, that the shortest path from this point to this point is exactly the geodesic. Okay, I'll stop there.